Linear dynamic systems are predictable and orderly, but when encountering high amplitude forces, severe friction, or sudden snaps, that predictability fractures. A linear system obeys the principle of superposition. This means the relationship between cause and effect is strictly proportional. If you double the input, you exactly double the output, and separate responses can simply be added together. In a nonlinear system, the principle of superposition does not apply. You cannot add two inputs to predict a combined output. Small disturbances can cascade into massive, outsized reactions. This graphic compares the general algebraic forms of ordinary differential equations. The first is linear, relying entirely on constant coefficients. The second equation is nonlinear, meaning the system's own changing state continuously dictates its ongoing behavior. For linear equations, the steady-state response is unique and mathematically clean. Regardless of where the system begins its motion, it will ultimately settle into a single, predictable state. Because superposition fails in nonlinear equations, we lose the ability to construct a general analytical solution. Tracking individual trajectories isn't enough. Grasping global behavior requires a shift in perspective, moving away from timelines and toward the geometry of the system itself. A nonlinear system can exhibit multiple distinct modes of behavior simultaneously. The exact outcome depends entirely on its initial state vector, the precise position and velocity of the system at time zero. This means a single system can possess multiple equilibrium points. Depending on where it starts, the system might rest in one position or bypass it entirely to lock into another. Certain initial conditions force the system into a limit cycle. These are isolated, self-sustaining periodic orbits where the system oscillates endlessly with a fixed amplitude and frequency. This plot illustrates deterministic chaos. In this regime, microscopically slight shifts in initial conditions lead to wildly divergent, unpredictable paths over time. In linear systems, complete stability is defined easily by a constant system matrix. Nonlinear systems discard this certainty, introducing complex and highly sensitive behaviors. To mathematically guarantee the behavior of a system we cannot explicitly solve, we must abandon the standard time domain. Instead, we map the differential equations into a topological coordinate space called the phase plane. Theoretical mathematics must describe physical reality. Consider a classic pendulum clock, which operates as a real-world nonlinear oscillator. To analyze this mathematically, we perform a state-space conversion. We reduce an nth-order ordinary differential equation into a set of n-coupled first-order equations. For this analysis, we isolate the two-dimensional autonomous case. Here, the differential equations do not depend explicitly on time, serving as the standard framework for observing dynamic motion. This diagram maps a physical mass spring system alongside its mathematical counterpart. We plot physical variables onto a two-dimensional coordinate system to define state variables. The horizontal axis represents precise position, and the vertical axis represents velocity. Any single coordinate plotted on this plane describes the complete instantaneous state of the system at a precise moment. State-space conversion successfully translates these complex differential equations into a navigatable geometric map. This graph maps the vector field. Calculating derivatives at any coordinate generates a velocity vector pointing the system to its next state. Tracing these vectors plots the complete system flow as time progresses. Autonomous systems are strictly deterministic. Because the rules governing the motion never change, the phase trajectories can never cross one another. The overall geometry reveals global bounding behaviors, clearly divided into convergence areas where the system stabilizes and divergence areas where it escapes. Within this flowing map, there are specific nodes where the vectors cease to point anywhere and all motion stops. These are mathematically defined as singular points, or equilibrium points. At these exact coordinates, the vector field evaluates to zero. These equilibrium points act as topological anchors. Their specific properties dictate the shape, direction, and flow of the entire surrounding vector field. Visualizing the map is highly useful, but we need a mathematical tool to classify the stability of these singular points without relying on a graph. We use local linearization and compute the Jacobian matrix, evaluating it strictly at the exact coordinates of an equilibrium point. If all calculated eigenvalues of the Jacobian possess negative real parts, the equilibrium point is locally asymptotal, generating repulsive behaviors like saddles or unstable nodes. The Jacobian works by constructing a perfectly flat linear tangent plane. This plane acts as a local approximation of the highly curved nonlinear manifold at that specific spot. However, this method has a critical failure condition. It collapses when evaluating non-hyperbolic points. If the real parts of the eigenvalues evaluate exactly to zero, such as in a center point, the flat linear approximation cannot determine whether the true nonlinear system is stable or unstable. Local linearization is a precise but narrow tool. To guarantee stability across the entire system, we need a rigorous mathematical framework that does not rely on local approximations. This text outlines stability in the sense of Lyapunov. It provides the definitive method for proving system stability when local linearization fails. Instead of tracking exact positions over time, Lyapunov stability establishes strict mathematical boundaries of containment. Translated into geometric intuition, around an equilibrium point at the origin, we establish an outer boundary, R, and a smaller inner boundary, R. The condition states, for any required outer boundary, R, we must be able to calculate a starting boundary, R. If the system starts inside the inner boundary, its trajectory might wander erratically, but it is guaranteed to never cross the outer boundary. If that wandering trajectory eventually spirals inward to rest perfectly at the origin, the system achieves asymptotic stability. This definition reframes the engineering problem. We stop asking, where is the system at time t, and start asking, can we mathematically guarantee it will never exceed our safety limits? To prove that a system perfectly obeys these containment boundaries, we use Lyapunov's direct method. This 3D plot visualizes a generalized energy-like scalar function, v of x. For the proof to work, the function must be positive definite. The geometric bowl slopes strictly upward and away from the origin in all directions. Second, the time derivative of this function, evaluated along the system's trajectories, must be negative definite. Physically, this proves the system's energy is strictly dissipating. With energy constantly draining, asymptotic stability toward the origin is mathematically guaranteed. Phase plane topology provides the geometric intuition for nonlinear behavior, while Lyapunov theory supplies the rigorous mathematical proof. But an engineering limitation remains. Proving a system is stable is entirely different from quantifying its exact physical behavior. High-stakes infrastructure, like spar-type floating offshore wind turbines, undergo massive, non-predictable environmental stress. Analyzing these structures requires extracting high-fidelity results out of strongly nonlinear dynamics. With our topological and stability groundwork established, we can now deploy analytical approximation methods, specifically perturbation theory and harmonic balance, to extract the precise results necessary for engineering design.